Alright, so the first thing that I want to do is to talk a little bit more about electronegativity and the formation of covalent versus ionic compounds. And the major thing that I want you to think about when you're thinking about covalent and ionic bonding is that it's a continuum. There's no distinct break line between an ionic compound and a covalent compound and the bonds that they're forming. So we said that ionic compounds or ionic bonds are formed when the atoms donate and accept electrons. Covalent bonds occur when the atoms are sharing electrons. And we said that there's two types of the covalent bonds. There's polar covalent and there's nonpolar covalent. The polar covalent bonds occur when they don't share equally, and the nonpolar bonds occur when they do share equally. So if we think about them on a continuum, we're going to use electronegativity difference. We're going to use electronegativity difference to determine this continuity and when things are going to form an ionic bond versus a covalent bond. So if our electronegativity difference between the atoms involved in the bond is less than 0.5, so it's going to be on that side of our continuum, this is where we're going to have nonpolar covalent bonds. So if our bonds are between 0.5 and 1.7 in their electronegativity difference between the atoms involved in the bonds, this is where we're going to get a polar covalent bond. And when we're above 1.7 in the electronegativity difference, this is when we're going to predominantly start seeing ionic bonds. In some textbooks you might see this number a little bit higher. You might see it at 1.9. So this is just an estimate, and it's a continuum where electronegativity difference is being used to predict how our electrons and our elements are going to interact. So there's a little bit of flexibility. It's just our guideline that we're using. But we can see examples from this. So a good example of a nonpolar covalent bond would be a carbon bonded with hydrogen. So when carbon and hydrogen are bonded, the electronegativity is going to be, so let's write that down here, carbon and hydrogen is 2.5 for carbon and 2.1 for hydrogen. If we take the difference, we'll see that our difference is 0.4. And so that falls in our nonpolar covalent range. A good example of a polar covalent bond would be when carbon bonds with oxygen. So carbon again is going to be 2.5, and our oxygen is the more electronegative partner in this case, up at 3.5. And so when we take the difference, 3.5 minus 2.5 is going to give us the difference of 1.0 in this case. And so that's going to fall within this continuum, and this is going to be partially negative. So the atom that is more electronegative has the electrons more of the time. It has more attraction for those electrons. And this carbon is going to be partially positive because it has the electrons less of the time. The oxygen is hogging the electrons. And then our sodium and our chlorine are very good examples of when we have an ionic bond that's occurring. So the chlorine is up at 3.0 in its electronegativity value. So chlorine has 3.0, and the sodium is at 0.9. So the difference between these two guys is going to be 2.1. So our difference equals 2.1. And so that's going to be higher than 1.7. So our sodium and chloride are going to be a good representation of our ionic bond. Another easy way to recognize when you've got an ionic versus a covalent bond is to just look at the periodic table of the elements. So when you're looking at the periodic table, if you have a metal plus a nonmetal, this is going to be very indicative of having an ionic bond. So when we have ionic bonds, they are usually a metal plus a nonmetal that form the ionic bonds. And that's because this is where you see the greatest difference between the electronegativity values. That's going to give you the strongest tendency for the metal to donate the electron to the nonmetal. So the metal is generally the cation, it's the donor, and the nonmetal is the anion component. And we can see that we are going to have typically 3 different types of substances that are going to come out of the ionic bonds. We're going to have salts, we're going to have acids, and we're going to have bases. So these are our 3 major things that are going to come out from our bonding. So essentially we are going to define a salt as an ionic compound that does not contain H plus or OH minus as the cation or the anion. That's a pretty simple definition. So examples of salts that we've talked about: sodium chloride, be a good example. Magnesium sulfate, another good example. Ammonium nitrate. Essentially any ionic compound that you can make that does not have H plus or OH minus in it. Our acids have H plus acting as the cation or proton. Our bases have OH minus acting as the anion. So a good example of an acid would be HCl or H2SO4, things that have H in the cation position of the molecule. The one thing though that I want you to note is that our electronegativity differences are not always quite spot on. So if we're looking at HCl, this is actually a covalent molecule, but the behavior of the hydrogen is a little bit fickle because it's also in group 1 of these elements, and so it can also act as a cation even though it's not necessarily predicted by the electronegativity. So our electronegativity for the chlorine is 3.0. Our electronegativity for hydrogen is 2.1. And so if we take the difference, this is going to be 0.9 as the difference. So we would predict that this is going to be a polar covalent molecule, right? But in this case, hydrogen is acting as the cation. If you put this in water, it will dissociate like an ionic compound. So our electronegativity differences are a guide, but they don't always reflect the behavior of the compound. So acids act like ionic compounds, even though they're predicted to be polar covalent compounds when you look at electronegativity difference. So they're kind of special in this case, and that's because hydrogen is kind of unique in its activity. It can act both as a metal and a nonmetal, and so it's an exception to our rule. So you just kind of have to take that with a grain of salt. If the hydrogen is located in the cation position and it's located first, it typically is behaving like the ionic compound and it will behave like an acid. The only acid that we don't see it written in that format is the acetic acid, so CH3COOH. In this case, this is the acidic hydrogen, and you just have to memorize this one. This is the only one that will be like that we will see, the carboxylic acid functional group. is very important for biologic systems, and this is an acid group. That hydrogen can be lost just like an ionic compound. Typically, if hydrogen is behaving like a covalent molecule, because it can do that too, it's got those properties, it's going to be written after in the following position. This is the one exception for the acids. This is an acid. Any other time that you see hydrogen written after the other atom, it's going to be behaving like a covalent molecule. So when it's in this polyatomic ion as the OH minus, it is connected to that oxygen in a covalent bonded position. If you put that in water, the hydrogen can't fall off of the oxygen because it's sharing electrons. They can't separate from each other like ions can. So hydrogen can behave like a covalent molecule. It can also behave like an ionic molecule. When it's written in the cation position, it's going to behave like an ionic molecule, except for acetic acid. This is the one you have to remember. All other times, when it's behaving like an ionic molecule, it's placed in the cation position. When it's behaving as a covalent bonded molecule, it's placed next to it on the other side. So when it's bonded to the carbon here, you've got CH3. These guys are represented as a covalent linkage to that carbon. The only one that's acidic in this case is the one on the carboxylic acid, and this is a special case for biologic systems and biologic acids. You just have to remember the carboxylic acid functional group. So bases then are going to have the OH acting as the base, and this is acting as the anion in the molecule. So anytime that you see OH in your ionic molecules, you're going to know that you have a base present. So in this case, you might have sodium hydroxide, or you might have magnesium hydroxide. But anytime that you've got OH at this position, you know that you have a base present. So for the exam, you should be able to recognize whether you have an acid, a base, or a salt present.